Hello everyone. Today I talk about the measure 0, which is depends on the possibility of the Riemann integral. In order to explain our protagonist measure 0, I'll explain some examples of the Riemann integral. This is clearly relate to our main concept. So let's see two examples. The first example is plotting graph. If to describe this graph as a formula, I define some definition. I x minus a following graph. If x is smaller than a, spew out 0, and otherwise the value, otherwise x is more than a, then spew out 1. And based on this information, if I write the name of the graph fx, given domain f is 0, 1 to the real number, the graph is first I x minus an, where an is a sequence defined. Originally, if a is in this case the fixed number, but in this case this is a sequence. The sequence name is 1 minus 1 over 1 plus a. For example, sorry, this is not a, this is natural number n. For example, if n is 1, a1 is 1 over 2. This is a1. And if n is 2 equal to 1 minus 1/3, this is 2 over third. 2 over third, this is mere. In a similar way, we can setting this sequence. And we know if n goes to infinite, the limit of an is clearly approaching 1. So this goes here, 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 This sequence is bounded in the given domain. So if we, based on this information, if we define this describe the graph, I already know the answer. The function is defined as first multiply 2 over n by 2 to the minus n, and take the sigma from n equal to 1 from 1 to infinity. So given the domain, if define the function, this graph is describe the graph. Let's check this case. Of course, I forgot. an is 1 minus 1 plus n, and ix an is the piecewise function, as I already said. Okay. For example, if n is equal, let's directly expand the sum. Then this is 2 over 1 I x minus 1 over 2, and next term is 2 to the minus 2 I x minus 2 over third, and the third term is 2 to the minus 3 and x minus 3 over 4, and so on. Okay, then if x is smaller than 1 over 2, the result is clear, because it will define if x is smaller than n, spew out 0. Okay, but x is smaller than n, more than n, spew out 1, and multiplying a half this if x is more than a half, this graph here, plotting here. Important point is that the given point is not defined, but this point is defined, the definition of the function. And if you consider the next term, in this case, if x is more than 2 over third, spew out 1, but multiplying this here, this guy's here, if x is larger than 2 over third, this graph, this term goes to 1 over 4, okay? But important point is here, this is a summation. So, consists of a summation. So, x is larger than or half, the value is still 1 over 2, but x is more than 2 over third, accumulating this value, 1 over half. So, this is goes to 3 over third. The result is the value 1 over 2 and the value 1 over 4, a quarter. So this is the 3 over 4. And if x is smaller than 2 over third, remarkable point is if x is smaller than, okay, if x is smaller than 1 over half and 2 over third, in this range, this is still 1 over 2. Because x is smaller than 2 over third, the accumulated, but already if x is more than 1 over 2, half, this is still 1 over 2. So this graph is plotted. Okay, let's see where deep thinking or the definition of x minus an. This is clear result. Okay. Similarly, we can, if we consider this term, if x is more than 3 over 4, this value goes to 7 or 8, because accumulated this here, and this here. So this is the value this 7 over 4, the summation of these guys, and x is if x is smaller than, x is larger than 2 over thirds, less than 3 over 4s, this value goes here. Of course, this point is discontinuous. For each point is discontinuous. So, because I said this value is this sequence is convergence to 1. Okay, the limit an goes to the 1. Every sequence, collection of a sequence is bounded of this bounded. So the graph is plotting this form. Now I then suggest some question about you. The question is here. I claim is here. This is a Riemann integral in the given domain 0 to 1. This means we can evaluate. This is possible to evaluate fx dx. The answer is yes. This is clearly a Riemann integral, so we can evaluate the answer. But the important point, the reason is in the previous lecture 12. This function, because this function is originally the function is the here. This function is the monotone function. Okay, so the graph here, 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 here. This intuitively the monotone function in the given interval. In this case, close the interval 0 to 1. So anyway, it looks strange. Even this continuous point, in this case, this continuous point, if we count this continuous point in this function, this continuous point, the sequence depends on the n. This continuous point, if we count this continuous point, this is the LF0. So this is the this continuous point is countable, denumerable case. Denumerable, and this continuous point, number of this continuous point correspond to the natural number 1, 2, 3, 4. Okay, because the sequence is given. Then important point is, even though this continuous point, if the function is given, even though this continuous function is denumerable, if the function is the monotone, then this is clearly Riemann integrable. I ask you a question. The question is here. F is the Riemann integrable on the given domain. This means if this is true, we evaluate from 0 to 1 to 1 fx dx. If it's possible. The remarkable point is here. In fact, this is Riemann integrable. This is true because in the previous lecture, this function is monotone on the given domain closed interval 0 to 1. Because this property, f is anyway Riemann integrable, and we can evaluate the value. The value is, we intuitively think, intuitively thought, this is the area of each the plotting here. Okay, important point then, but however, important point is that even though this is integrable because of the monotonous function, this has very many discontinuous point. Very many discontinuous is so informal, we can say when you consider the sequence, when considering the sequence, this has the function f has the numerable so this number, this continuous point is correspondence to natural number. So cardinal has cardinal 0, okay? F has the numerable discontinuous point. But even though f has the numerable discontinuous point, because in the previous lecture 12, this is anyway monotone function. This is anyway Riemann integrable, and we can evaluate the value. Then, in this, when considering this point, we should doubt that if just the function is given, even though if the function is not monotone in the specific domain, just if f has the numerable, if just the numerable discontinuous point, is it possible to evaluate integral? In other words, the Riemann integral. This is our first question we must have. In this lecture, I'll explain the discontinuous point, between the relation discontinuous point looks like this, and the Riemann integral, possibility of Riemann integral. And let's consider another example of in order to approach the motivation of the method 0. This is the familiar function. It's a constant function. Y is equal to 1. And this is clearly continuous function. So if this is clearly Riemann integral, 1 dx, or just written dx. This is clearly, we understand intuitively, this is the area which is surrounded y is equal to 1, x-axis, y-axis, and x is equal to 1, which is perpendicular to x-axis. Here, or ftc is no problem, but in this case, this graph is suggests intuition of the value. This is just 1. Okay. And I'll make, as we in this case, this is clearly continuous function, but I'll make an arbitrary an arbitrary point and make this function is discontinuous. As compared to this case, this continuous point is already given. But in this case, I will make this continuous point using arbitrary point. So if I pick x0, and then this is this continuous point, but so this value is punked. This is not defined on constant number 1. Instead, I will make this point is the value of the x0. This is 0. Okay. Then this is clearly discontinuous function. And if we try to, I forget the notation, 0, in the previous example is also 0 to 1, and in this discontinuous function, I will explain 0 to 1. Then this is still 1. Note that this is clearly not monotone function. and this this is not continuous, and this is not monotone. So we can use we can decide from using previous theorism, we cannot decide whether this function is integrable or non-integrable in the Riemann sense. But we just check the definition of the Riemann integral, definition of the Riemann integrals. So if the function is fx, and if the function f is contained 0, 1, means the lower sum f and upper sum f is coincide, then we say this is the Riemann integrable, and this is the value of the integral from 0 to 1. Okay, so we can check this here, the coincidence, lower sum, and lower integral and upper integral. I delicately calculated this here, but this is clearly same value. In case the problem in other area, if the interval is for convenience uniform, so this is in this case n over n, and because in this case the lower sum and upper sum is same, because the length is the uniform, and the height in this case, in case of infimum case, infimum and supremum, the length is the same, because this is constant function. Okay, so without this continuous point, the rectangular area in case of the infimum, there's a lower sum and upper sum is the same. But the problem is here. In this case, because when infimum, the length of infimum is 0, because this is the infimum value on this given interval. But in this case, supreme case, this height is a supreme value of the length. This is here. So the difference of the area only this continuous point. But if we indeed calculate the total sum, this value, this point, this rectangular between the red infimum and blue supremum does not impact the value. So we check this is the same value, and we can define this value is well defined, even though one point is discontinuous point. Then let's we have a brief. This means repeatedly we construct this continuous point like this. So this is just one point of this continuous point in this case. Then I pick another point x1 and similarly make this continuous point. But indeed, even though the calculation is a little complex rather than tedious, this is also Riemann integrable. Even though the one point is discontinuous, 2 points in this case, 2 points, even though 2 points are discontinuous, then this is clearly Riemann integrable. This means lower sum and upper sum is coincidence. Now suppose that there are numerous of this continuous point exist on the given interval, but numerous gigantic it is not informal word in mathematical field. So in this case, I recommend these words, finite. This continuous point is finite, but consider finite point is sufficiently larger than uh, can we can think. So this prodigious point such that this continuous point is 1 billion, 2 trillion, like this. Okay, then in this case, this is the Riemann integral. And another word is denumerable. Denumerable set means set is the cardinal. Okay, the set is equipotent in the natural number. So, for example, rational number q is the numerable set because each member in rational number we can count. This means we number each rational number. Okay, so of course n itself is naturally the numerable set. Okay, so if this continuous number is the numerable, in this case, in this given interval, find the rational number on this given interval. This is clearly the numerable set. Okay. Then, if this continuous point has all of the member in this point is this continuous point, then this is Riemann integral. And another question, if non-denumerable case, if this continuous point given interval is non-denumerable, for example, relational number is non-denumerable. Non-denumerable means the set does not match a natural number. Okay, so in this case, irrational number, you cannot count the irrational number because irrational number does not. If we try to matching the natural number, okay, this corresponding contradict. So in the set theory, the irrational number does not match each natural number. So that cannot count irrational number. And okay, if the given interval, if all of the irrational number is this continuous point, is dense and integrable. Okay. The critical key to solve this problem is this concept, the definition measure zero. When if we run the concept, if we know the measure zero, then this theorem, Lebesgue's theorem, answers the question. So let's go back and let's study the measure zero. So the definition of measure zero, is here. Let epsilon be given a subset of E of real number has measure 0. We call E is measure 0 when if there exists a countable correction of interval, open interval, such that this interval contains E, covers E, and the length, the total length of which covers in E is E, set E, element in E is smaller than epsilon. So this means for any epsilon is given, we always the length total sum of lengths is always smaller than epsilon. This means again because this for any epsilon any epsilon can be given. So if the epsilon is sufficiently small, we think, then anyway the length is less than epsilon 0. So the length is approached to be 0 when considering the definition of the measure 0. We can shrink the length we desire because any epsilon given, even though very sufficient real number is given, we erase the sum of lengths is smaller than epsilon. So this is the definition of a measure 0. If we do this action, if we make this set E, then the set E is called a measure 0. So for example, in the previous example, we did the two discontinuous point is the Riemann integral. Okay, so I set X, the whole set is the given interval, closed bounded interval 0, 1, and E is the 2 point x1, x2. Okay, for examples here. Then when I draw the figure, closed interval 1, and I delete arbitrary point x1, x2. Then I claim clearly, the claim is the set E is measure 0. Measure 0. To do so, we should take the interval in which covers each set element in E. So I'll wrap these two guys here and here. One is blue, one is red, pink. Okay, then and to do so, and okay, let epsilon is clearly given. Then using this epsilon, we make this range of interval by using the epsilon value. This means 1 is x1 minus epsilon of 8. Important point is 8. Okay. One another is x plus 1 epsilon over 8. This is also same like this. This interval is given. The reason is to satisfy this condition. So then if we calculate the ranks, okay, this is countable correction. Countable, I referred means countable is, I do not refer this here, okay, finite or denumerable. So in this case, the previous example, finite or denumerable case is altogether called countable case, countable set. Okay. Then, okay, this is in this case, the interval is finite, also countable correction. So, first condition clearly, the union I1 union I2, as you see clearly, covers the two set E. And if we calculate the ranks, Li1, Li2, the ranks is defined just the difference of these two guys, 2 points. So this is just if we then x1, x2 is vanishes or these guys vanishes, and so remain each say one is just subtract this value, then this is epsilon over 4 fourths, and this is also epsilon over fourths. This result is epsilon of second, and this is clearly smaller than epsilon. Then the important point or important example, one of the important examples in this which is related in this lecture is, suppose E is a countable set. This means I referred countable means finite or denumerable, two case. Then claim is that E is a measure 0. E is the set E, the collection of countable set. For example, natural number. Natural number is case denumerable set, and finite free prodigious element discontinuous point. For example, let's say 1 trillion point on the given interval. However, this is measure 0. So to satisfy this claim, in case if the set is finite, E is the finite, then we consider the set E is consist of xi from I1 n. Even though n is sufficiently large, then this is anyway finite. Okay. Then we can, and then we consider the length which contained in. So let's suppose in in this case x ik, okay, ik, which contain each set. This is the open interval for all kn, for in this case, this here. For our k, let's suppose xk minus epsilon 2 of 2k1 and xk plus epsilon of half 1 over 2 to the k. We just setting this point is important because we finally deduct all of the sum of lengths is smaller than epsilon. Okay. For each component, xk, xi, if we ik the interval, this is such defined. Clearly, all k element xk contains in each interval. Okay. Then this first condition is satisfied because so ik the union of interval is clearly all element in E. Each element xk interval wraps around this. This corresponds to this. And this corresponds to this. But the important point is that when the number is bigger, subscript is bigger, then the interval, open interval, is shrink. It's like this because these properties. And if we consider the ranks, the summation of ranks, LIN, this is just K1 because this is finite, and the result is the 2k 2 to the k plus 1 to epsilon. So this is epsilon over 2k. This is geometric series. If epsilon is out of the sigma, this is half to the k. And the formula is the ratio is half, so ratio comes here. One of half comes, and the first term is also 1 over half, and the ratio is here. The total n times number, so this comes to n, and but in this case order is 1 minus half to the n, this here. If we calculate this here, this vanishes, and epsilon 1 minus half to the n. But these guys is always less than 1. Okay, 1. Its value is always smaller than 1. So our proof is finished. So this in case of finite case, this is clearly measure 0. And in case of if E is countable, denumerable, if we think if n is large, if n is correspond to the natural number, we can match the natural number. When considering this based on information, just change this point, these 2, just replace 4. Replace these 2 with 4. Then this is 2k2, and this k plus 1, this here, and this here, and this here. The reason is here. If k is 2, this guy is 2, the denumerable case is just change. This is the infinite, okay? So in this sequence, we just goes to goes to infinity. But if this is 2, if we n goes to infinity, epsilon, the result is the epsilon, okay? So this is not satisfy our definition. But if we setting this is 4 and goes to infinity, this value is epsilon, or half of epsilon, okay? Half of epsilon. This is smaller than epsilon. So in case of the denumerable, the definition of when considering the definition, just change this here. Change the value 2 instead of 4 instead of 2. Then our claim is also satisfied. In this case, goes to infinite, okay? Or change the notation is infinite. And just go, in this case, just goes to here, not using this formula. Okay, this goes from here, and our proof is finished. Now let's see the Lebesgue theorem. A bounded real interval function on a B is Riemann integrable if and only the set of this continuous point f has measure 0. This means if we consider the set E, this E is the closed interval in a B, which correction f this is discontinuous point. X is discontinuous point. Discontinuous point. The given function f closed bounded interval goes to real number. Then, if this set is the measure 0, as I referred this, then this is Riemann integrable. This is Lebesgue theorem. The proof is very complicated in this lecture, so I omit the proof. But this, rather than proving proof, this is more important. The application is more important. For example, if we know this theorem, we can answer the question. If the discontinuous point is finite, even though prodigious this is Riemann integrable. So this is yes. This is the Riemann integrable. And the numerable is also Riemann integrable. In fact, this is countable set. Countable set is I already said measure 0. Okay, so this is clearly measure 0. But in this case, because this is not because it's non-denumerable, okay, non-denumerable set, so we can vouch for, we cannot use this theorem. Then we directly investigated this property, but this is not integrable. So short point is that if the countable set is if the discontinuous point is countable set, we always, even though the discontinuous point prodigious and the discontinuous point is the cardinal, the set of cardinal of this continuous point is the natural number, same as natural number. This is integrable, Riemann integrable. Okay, and these examples, this is originally this because this is function monotone. Okay, this is because it's monotone. This is in fact this is actually Riemann integrable. So this evaluate this value integral. But important point, this is the numerable discontinuous point. Okay, however, this is no impact to integral, to evaluate the integral, because this point, this continuous point is measure 0. So we can remove some suspicion why this has some countable discontinuous point. Why is it integrable? But this is no problem because this is denumerable, countable. This function has countable discontinuous point. Okay, so this is no problem. And of course, this theorem, by this theorem, this is clearly a Riemann integral. Another example I want to discuss about is a domain function. This function is given from here. First, easy point is all irrational number is 0, because irrational number is non-denumerable. So we can see lots of irrational number exist on the irrational number, because irrational number is non-denumerable, and other case this is countable. So we can, if we compare the concentration, irrational number fills this given interval, whereas the rational number does not, the little concentrated than this irrational point. Okay, so, and if in case of a rational number, all of the rational number can be expressed as fraction. Okay, then all of the fraction type just derive the numerator only arrive. Okay, so if consider x is a half, then this is just okay. This is just a half. Then if x is here 1/3, 2/3, this value all goes to this here. So 1 is here, 1 is here. Okay, and x is the numerator is 4, 1/4, a quarter is here, this here. Then this is all goes to a quarter. So this is here, this is here. But note that this point is 1/2. I forget this condition. All of the member greatest common divisor we can consider only 1. If this case is corresponding this, we just this here, okay, this here, this here. This is not a function, okay, because one value correspond to one value spew out two value to input to output. So this is not a function. So we only consider greatest common divisor is only 1. So this is not our case, and this comes here. This is also a quarter. Okay. In similar way, we corresponding this here. When the numerator is bigger, there are lots of the fraction also flat from this graph. Okay, but I claim that this function is a little complicated, but this function is also Riemann integral. The reason is clear. This continuous point is the correction, okay? Correction of this continuous point is measure 0. So the point, most of the point reside in the irrational number, okay? But in this point, this point is discontinuous, okay? But this continuous point is the rational number, okay? This continuous point is rational number and the intersection of the interval. This cardinal is countable. I left 0. Okay, so this because this continuous point is the countable set. This continuous point to countable set, and this guy is the measure 0, and Lebesgue's theorem. This is Riemann integral. It's condition if and only if condition, okay? Because this continuous point measures 0, then this is Riemann integral. And again, let's see the non-denumerable case. Okay. This is clearly not Riemann integrable because the upper sum and the lower sum is different. In case of the countable case, it continuous is countable point is by the Lebesgue's theorem. This is always in Riemann integrable. The countable set is this continuous point is the countable set. Okay. Then in this case, we observe in this case. In fact, this case is expressed here if the x is the rational number is 1 and irrational number on this given interval, because the interval is 0, 1 is here. When you consider, because this is denumerable, this is denumerable and this is non-denumerable. If we draw the plot, this has numerous holes. Portray the graph, and this has many. Okay. In this case, irrational case is a rational case. But important point is that this is not Riemann integrable. But I want to this. But consider. Think that this is no problem if we consider the integral value is just 1. But in the Riemann sense, because this value does not exist, because the infimum, the upper sum of the integral and the lower sum of integral, upper integral is not the same. But I want to claim that this is also integrable. This function is also integrable, and the value is the 1. I want to evaluate. But this is because in the Riemann sense, because by this property, by this here, the Riemann integrable does not exist. But it is no problem. The value is just 1. But how to say this value is the 1 in the problem limitation of the Riemann integral? The answer is consider new method of the integral. Newly define the integral. The integral is said Riemann integral. So if we study the Riemann integral, the Riemann sum is just using the partition of the interval and multiplying the rectangular. So in case of the Riemann integral, in the previous lecture, we consider the rectangular, the infimum, and the height is the rectangular is the infimum and supremum, and goes to limit, and the rectangular, the upper sum and the lower sum is the coincidence value. Then we can coincide the value, then we can say this is the Riemann integral. But the Riemann integral does not define in such a way. So if we define the Riemann integral method, then we can evaluate this integral value. In the Riemann sense, the value is the 1. Because this Riemann integral does not define the upper sum and the lower sum in like this. So To understand of the Riemann integral, we concentrate on the measure. This measure. So it's measure theory. So in this lecture, I will explain what is the measure. I will just deal with the measure is only 0. But next lecture, I will define and introduce what is the measure and measure space, and then I will define what is the measure. Measure is the one of the function type of the set function. But next lecture I'll explain detailedly.